Welcome back, and we are studying Chapter 4, Effects of Electric Current, Standard 10. So before we start with the effects of electric current, let us understand what are good and bad conductors. Good conductors allow the passage of electric current that happens when electrons start flowing. Metals have more free electrons, 1, 2 or 3 in the outermost shell. So they easily are able to donate those electrons, and those electrons are free to move about. On the other hand, the bad conductors are also called as insulators. They are bad conductors because they do not allow the passage of electric current. That's because they do not have free electrons. Normally in their outermost shells, they have 5, 6 or 7 electrons. Because of that, it is very difficult to give away electrons. The electrons are held tightly towards the nucleus. Okay, so all metals are good conductors. Among the non-metals, there's an exception, and that is carbon. Carbon electrodes or graphite. Okay, that is the only exception of non-metals, which is a good conductor of electricity and in fact used in many cells or batteries. Among the insulators are all non-metals. Non-metals, asbestos, rubber, glass, plastic, all these can be examples of bad conductors, and as they are bad conductors, they can be used as insulators. Now, there's a good reason here. Though iron is a good conductor, we do not get electric shock when we pick up iron resting on a ground. Let's think about it. Okay, now look at this picture which we studied in Standard 9. Okay, and here what you find is the metal wire or a piece of an iron which is not conducted to a cell has electrons, free electrons, which can just move around themselves. Okay, that is just between the spaces around the atoms. So they move just randomly. That does not generate electric current. For electric current to generate, there has to be a continuous flow of electrons in one direction. And that happens, look at the second picture here, only when you connect it to a cell. So when it is connected to a cell, positive and negative terminal, electrons start flowing from a negative terminal to a positive terminal, and as electrons flow from negative terminal to positive terminal, electric current is generated, and it flows from positive terminal to negative terminal as conventionally stated. Okay, so for electric current to pass, electrons have to move. Okay, there has to be a continuous flow of electrons, and that becomes possible when we connect it to a cell or a battery. Then let's revise some of the important terms, units and formulas. Okay, now the first one that we studied last year was voltage, which is very, very important to understand the effects of electric current. So voltage, also called as potential difference. What is potential difference? It is the amount of work done. It is work to carry a unit positive charge from a positive terminal or from a point A to point B, to a negative terminal. Okay, and therefore potential difference is actually work done to carry the charge. So W upon Q, work upon charge. According to Ohm's law, which we study in 9th standard, if the physical state of conductor remains the same, then the current flowing through it, I, is directly proportional to the voltage. From this experiment, okay, we can get the formula voltage is equal to current into resistance. This is a little revision of what we did in the 9th standard. If current is directly proportional to voltage according to Ohm's law, then to remove the sign of proportionality, we took a constant K. Okay, then that constant K, 1 upon K, turned out to be the resistance offered by the conductor. So we got I into R is equal to V, that is V is equal to I into R. Okay, so you have two formulas. Whenever we solve any problem, we need to remember what is given, what is asked, and accordingly we need to use the formula. If current is given, we cannot use the formula V is equal to W upon Q. Then we have to use the formula V is equal to I into R. Okay, that is voltage, potential difference is equal to current into the resistance. Then what is current? It's Current is the flow of electrons through a conductor. Okay, so it can be measured as the charge carried per unit time, a unit charge carried per unit time. Therefore, current is equal to I, that is the symbol for current is I. I is equal to charge, that is Q upon T. Then according to Ohm's law, which we just revised, okay, in the previous slide, we can go back to our previous slide. Okay, so we just studied Ohm's law. So from Ohm's law, we had V is equal to I into R. That means I is equal to V upon R, where V is the potential difference, R is the resistance. Then what is resistance offered by a conductor, or resistivity, which is taken as rho? This is also revision of the previous standard of standard 9. So resistance offered by a conductor is directly proportional to the length and inversely proportionate to the area. So therefore we get R directly proportionate to L upon A. To remove the sign of proportionality, we took a constant rho. Okay, that rho is actually the resistivity offered by the conductor, and it differs from metal to metal. Copper will have a different resistivity than gold or silver or aluminium. Also, depending on the thickness, a thicker copper wire will have lesser resistance as compared to a thinner copper wire. A longer copper wire will have more resistance compared to a shorter wire. So that way resistivity differs from metal to metal, from conductor to conductor, also according to length and the area of cross section. So that resistivity is given as rho. The symbol used is rho. Rho is equal to resistance into area upon the length. Okay, so rho is equal to Ra L. So R A upon L, and the unit for resistivity or resistance offered is ohm meter. Then this is a chart of a few of the units, symbols, instruments used and the formulas which you need to remember. Okay, try and learn by heart. Potential difference of voltage, that is symbol V. Current is I. Resistance or resistivity is rho. Power is P. Heat generated, which we are going to study this year, is H. Okay, heat generated is H. So the unit for potential difference is V. Current is measured in ampere. So A. Resistance or resistivity is measured in ohm, and ohm, yes, and power is equal to watt or joules per second. Okay, heat generated is, the unit for heat generated is joules. Then voltmeter is the instrument to measure potential difference, ammeter to measure current, ohm meter to measure resistance offered. And the formula we have just revised, V is equal to W upon Q, V work. We remember that way, V work, that is V is equal to W upon Q. But according to Ohm's law, V is also equal to I into R. Current I is equal to charge passing per time, so Q upon T. According to Ohm's law, I is equal to V into I. Okay, then resistivity, rho is equal to R into A, area of cross section, upon length. Power is equal to the energy upon time, energy given offered upon time. Energy is also the work done, so work upon time, but work done is actually the voltage. Voltage does the work in carrying charge Q, so V into Q upon T. But Q upon T is actually equal to current. Therefore, we can say power is also equal to voltage into current. That is potential difference into current. So V into I. Heat generated is equal to power into the time. How much of power is being used and for how long? That will give you the heat generated by electric current. So it is equal to power into time. Now power is actually equal to voltage into I, V into I, which we have just seen in the previous formula, into time. So therefore heat generated can be potential difference into current into time. So we stop here, and in the next video we will talk about the heating power of electric current, which is also called as Joule's law of heating. So till then, keep studying. Bye-bye.